Okay. So state what happens, if anything, to the following properties of the waves as they travel into the shallow water. Okay, so the speed will decrease.
Okay, so you know that it's about refraction if we talk about. So,
Yeah.
so how you can explain me refraction? The first thing is what happens to just don't go for refraction. Just you tell me if a wave enters from rare medium to denser medium, what happens to its speed basically
It decreases.
from like you say denser to rarer medium. I'm asking denser to rare.
Okay. Denser to rarer medium, it speeds up.
It's what? It's a speed up.
It
It speeds up. Yes,
yeah.
that's very correct. Now read this question and then tell me what happens to the speed and wavelength.
Um so uh okay, so it's traveling from a denser to a rarer medium.
Yes.
So it'll increase.
Okay. So it's what's mentioned here. Its wavefront A has reached the boundary between deep water and shallow water. Parts of wavefront B and C have already crossed into shallow water. The direction of these incident wavefronts is marked. So it's if anything following properties of waves has traveled into shallow water. So speed is definitely going to speed up. And then wavelength.
The wavelength will decrease.
Okay. By which
Or,
relation?
um, well, um, uh, when it passes, into the more rare medium, oh wait, well, so the wavelength will increase then.
Okay. First you tell me by which law you can say, like which equation will you apply, sorry, the formula.
Wavelength is, um, wavelength is lambda equals, um,
Okay, wait a second. This is actually moving, they travel into shallow water, right? From deep water to
mhm,
shallow water they are basically moving, right? So speed decreases.
yes,
Okay, speed decreases.
okay,
Yeah, because
yeah.
okay, now tell me about wavelength.
So from deep water to shallow water, it's the wavelength will decrease.
Yes, wavelength also decreases. Why? Because you can clearly see, I told you when I was explaining you refraction.
Hmm.
So it's like you can see screen, right?
Yeah.
Okay, so there's equation C is equals to lambda times f. That means your speed is equals to wavelength times
Hmm.
frequency. And I've told you when a light enters from one medium to another medium, it bends because change in density. That's basically refraction. And same thing is happening here, like when it enters from one medium to another medium. Clearly speed changes, wavelength changes, but
Uh huh.
frequency remains same. There is no change
Okay.
in frequency, and when there is no change in frequency, then you can clearly say that speed is directly proportional to wavelength. That means when
Okay.
speed increases, wavelength increases, and if speed decreases, wavelength decreases. Clear?
All right then. Yeah.
Now the next one is carefully complete the diagram above to show wavefronts B and C as they travel through the shallow water. So this is the wavelength B and C, and you have to complete that.
Okay. All right then. So complete the diagram. Right. Okay. Wavefronts B and C as they travel through the shallow water.
Yes.
Okay. So when uh
This
so
is the
when a
incident wave
wave
direction.
yeah
Yes, yes. So that
yes so yeah sorry
no, no, continue, continue.
okay so as they travel through the shallow water. Okay. So as the so when a ray goes from like a rare to denser no denser to rare medium,
Yes.
then it will bend um it'll bend towards the normal.
Away from the normal.
Okay.
Okay.
Yeah. Um right, so it bends away from the normal.
So you tell me, where will this go? Like if you have to complete the wave direction, where will it go?
It'll bend more towards the shallow water.
Like this one?
Yeah.
Yes, that's correct. And for this it will same, it will be same as well, okay? So this will also
Hmm.
go like this. So this is direction. And how you have to write the wave fronts, like see, if it's moving like this. So here also, like if you're taking, actually what's happening, you have to complete the diagrams by two different ways. See, if you read the
Hmm.
question completely, it's given as the diagram below shows the three water wavefronts A, B, C. This is water wavefront A, B, and C. Moving from deep water to shallow water. So basically they are moving from deep water to shallow water. Wavefront A has just reached the boundary. So it just reached the boundary here. Between the deep water and shallow water, parts of B and C have already crossed into shallow water. So this has already crossed, but it has just reached there. The direction of these incident wavefronts is marked and the normals of the boundary are marked N. So this N and M are marked as, you can say, this is a normal. N and M are the N and N are what the normals of this boundary. So what you have to do, you basically have to tell what happens to the wavefront as well. Okay.
Okay.
So the direction of wavefront, how can you explain the direction of wavefront?
The direction of the wavefront is well, it's
One thing is
like
that shallow water is a denser medium and deep water is a rarer medium. Okay.
okay,
Now think that this wavefront are moving from rarer medium to denser medium. How can you complete these two wavefronts?
rare medium to denser medium. Um, it will be bending um, the it'll be bending away from the normal.
Away is in the case when it moving from denser to rarer, but
Oh,
here they are moving from rarer to denser. Always remember, shallow water is denser one and deep water is rarer one. Okay,
okay,
then it's much easier for you to solve.
okay. So it'll bend to so it's going from a dense to a rare medium.
Yeah, it's moving from rarer to denser. Deep is rarer and shallow is denser. So it's moving
Okay.
basically rarer medium to denser medium. So it will, you see, both the wavefronts bend towards the normal. Okay.
Both.
To,
Okay.
so this, they will go like this and like this. Is this clear?
Yeah.
Honestly, it's clear. If it's not, I can repeat it.
It's clear, yes.
Okay. Okay, the next one is the long bar makes 24 vibrations in 6 seconds. Calculate the frequency of water waves produced. Include the appropriate unit in your answer.
Okay. So the long bar makes 24 vibrations in 6 seconds. Okay, so frequency equals 1 over t. So first we need to see how many we need to see how many vibrations are in 1 second.
Yes, that's basically frequency. How many vibrations in
Okay.
1 second?
Okay. Um so first we write out 24 vibrations in 6 seconds,
Yes,
and then we start canceling it down. So
yes,
24 divided by 6 is 4
yes,
vibrations
yes,
in 1 second.
yes,
Um, and we need to find the time needed for one vibration to occur.
yes.
Okay, so we cancel it down again. So we divide both sides by 4 because we're trying to find one vibration.
Yes. So what's your
So
final answer then?
one vibration in um, 0.25 seconds.
Okay, so your frequency is 0.2
Um,
hertz. You have to repeat.
no,
Yes, yes.
no. Sorry. That's I think that's the time. That's our time.
Okay. See, if you have to see the definition of frequency, so frequency is vibrations per second, which means how many times a particle is vibrating in a second, or how many waves are completed in a single second. Here it's given as that the waves are vibrating 24 times in 6 seconds. If they are vibrating 24 times in say 6 seconds, then in 1 second it's 24 divided by 6 vibration. Is this clear? Just I am applying unitary method. Okay.
Okay.
So
Uh
if
huh.
in 6 seconds it's 24, then in 1 second is 24 divided by 6. That will give you 4 vibrations. So this wave is vibrating 4 times in 1 second. And that is the frequency, how many vibrations per second. In a single second, how many times a wave is vibrating is its frequency. So basically it's vibrating 4 times in a given second. So its frequency is 4 hertz. Clear?
Okay. Yeah.
Now the next one. Using the information from diagram and your answer to part 3 from this part, calculate the speed of the wave waters in the deep water.
Okay. Right.
So you can
Yeah.
see the question as well, whatever the information is given.
Okay. Using information from the diagram and your answer to part 3, calculate the speed of the water waves um, in the deep water. Okay. The water waves in the deep water. Okay. So we've got the frequency, which is equal to 4,
Yes,
and we need this wavelength. Um, So the wavelength lambda equals
You have to use wave speed equation, okay?
okay. So speed equals um lam. Is it frequency times lambda?
Yes, that's very correct. And since you want to calculate speed, you have frequency. Now next aim is you should know the lambda, that is wavelength. And wavelength you can calculate from this diagram. So see the diagram and tell me how can you calculate the wavelength.
Okay. Um. The wavelength. Oh. Oh. The is it like okay? So there's like three waves,
Yes,
and the distance between the three complete waves altogether is 5 centimeters.
yes. And then how can you calculate wavelength?
Um, so wavelengths. So there's three complete waves, and they all like altogether it measures 5 centimeters. So we need the measurement of one wave. So we do 5 divided by 3.
It's 2. See,
Oh,
uh, if I draw this here, this is wave, like the transverse wave that we used to calculate. So it's like this, right? So this is
yeah.
whole one wave completed. This is whole one wave completed. Okay, and there's only one lambda in between it. This
Okay.
is the lambda. Same as it's 1, 2, and 3. So distance between this is the lambda, and distance between these two is lambda. So there are two lambdas, and total is 5. That means it's lambda plus lambda is 5, and lambda is 2.5 centimeters. So your wavelength is 2.5 centimeter. So distance between two
Okay.
consecutive crest and consecutive trough is lambda, and this is the distance between two consecutive ones, and that's why it's your lambda is 2.5 centimeters.
Okay. So lambda equals 2.5 centimeters.
Yes.
So okay. Now we calculate the speed. Speed equals F times lambda.
Yes.
Okay. So F times lambda. Um, F is 4 times lambda, which is 2.5.
Yes.
Um, so 2.5 times 4 is 10. So speed length is 10 meters per centimeters per second.
Yes. 10 centimeter per second. That's the correct one. Now, the next part B.
Mm-hmm.
Ultrasound is a longitudinal wave. Okay, so we know that sound is a longitudinal wave. So ultrasound is a longitudinal wave. Explain what is meant by longitudinal wave.
Oh, the particles vibrate in 90 degrees to the direction the wave travels.
It's transverse waves.
Oh, that's transverse. Oh, longitudinal. The particles travel in the same direction as the particles vibrate in the same direction as the wave travels.
Like instead of same, it's parallel. Okay, so it's not always that
Okay.
they move in the same direction. It can be in opposite, but they remains parallel. So direction is like this.
Okay. So particles vibrate parallel to the direction of the wave.
Yes. So wave propagates here. So particle moves like this and this. Okay, so it can be here at that time, it can be here at that time. And this is wave propagation, but in both the cases you see they are parallel. Okay, so instead of saying in same direction, you have to use parallel direction. Okay.
Okay.
That's correct, this definition. Now moving on to the next one. In what two ways is ultrasound different from audible sound?
Um. Okay. Wait. 1 moment. Let me just finish writing the answer down.
Okay, okay.
Okay. Um. Ultrasound is higher than 2000 hertz, which is the range of audible sound.
20,000, 20,000.
20,000 hertz.
Yes. So there are range. If we talk about the audible range, it's 20 to 20,000 hertz. Okay. And beyond
Mm-hmm.
that, we're not able to listen that. If we talk about infrasound, it's lesser than 20 hertz. And for ultrasound, it's more than 20 hertz. Okay. But it's written as in what two ways is ultrasound different from
Okay.
audible sound? So first, it's a frequency. And basically you can say that it's above the threshold, so basically yeah, it's different from audible sound. So it's basically its frequency, and second it's what its wavelength, you can describe it. But basically it mainly dependent on frequency actually. Okay.
Okay, so ultrasound has a higher frequency
Yes, then 20,000 hertz.
than 20. And it has a larger wavelength.
Not larger because they are inversely proportional to each other.
Okay.
It's the same. You have to apply every time the speed wave equation.
Okay. Um. Oh, it travels faster than audible sound.
Yeah, speed also differs, right?
Okay. Um. Has a higher speed than.
Yeah. And now the next. Yes, yes. Do you have any doubt?
Yeah. Yeah. So it has a higher speed than audible sound.
Yes.
Okay.
Okay, now the next one. Ultrasound used to measure the thickness of concrete block as shown below this. Describe how the ultrasound produces the sound peak shown on the screen.
Okay. Um. So the first peak is when as it penet is right before it penetrates the concrete block, and the second peak is after it like comes out of, of the other end of the concrete block.
Yes.
Okay, so the ultrasound produces a second peak shown on the screen. Um, it's produced as the ultrasound is coming out of the other end.
Yes.
Okay.
So, okay. Like this. So ultrasound is used to measure and this. So can you just repeat the last one, what you have explained me?
Well, it the second peak is the ultrasound like coming out of the other end of the concrete block after the concrete block has been penetrated by the ultrasound.
Yes, yes. That's very correct.
Okay, as the ultrasound.
So this would display how the sun produces the second peak shown on the screen. That's it. So basically, this one's correct. Now the fourth one.
1 moment, just like writing it down.
Okay. So even you can write it's basically because of the reflection. That's very correct. That you have explained. But in short, you can say that it's basically reflecting.
Okay. Reflected or refracted?
Reflected. Sounds reflected.
Reflected. Okay. Alright, number 4 then.
Yes. So it's number 4. The speed of ultrasound in concrete is 3000 meters per second. Each division on screen represents a time of 0.0005 seconds. Using the data, calculate the thickness of concrete block. Show clearly how to get your answers, starting with the equation you plan to use.
Okay. So, calculate the thickness of the concrete block. Each division represents a time of 0.00005 seconds. Okay, so each square is that many seconds. So between the first peak, there's 1, 2, 3, 4, 5, 6, 7. There are 7 squares between the first and second peak.
Yes. Yes.
Okay. So this is going to be like a speed equals distance over time.
Yes.
The thickness is going to be the distance.
Yes.
Okay. So distance is speed times time. Speed is 3000 and time is 0.00005 times 7.
Yes.
So let me just calculate that. Just need to get my calculator.
Oh.
3000 times 7 times 0.00005. The distance is 1.05 meters.
1.05 meters. Okay, so you have multiplied it. It's 3000 times 7.0005. Okay, so your final answer is point what?
1.05.
Okay. So your answer is correct, but the thing is, it's given as the speed of ultrasound in concrete is 3000 meters per second, and each division on the screen represents time, this one, okay? And you have
Okay.
to calculate the thickness. So, like the time that you are calculating is the total time. Is this clear? Total time
Okay.
of going and reflecting back, but for like to in order to calculate you have to calculate only the time to move from one point to another point, not the total time, only the time from one point to another point. That means you have to divide it by 2.
Okay.
Is this
So
clear, or like should I explain you with diagram?
no, it's clear. So okay, so what I had calculated was the total time for like
Yes, total
both like to
yes, you have taken the
okay.
total time. Instead what you have to do, you just have to divide it by 2.
Okay. Right. So 0.00005 0.005 times 7 um, divided by 2.
So what's your answer?
0.525 meters.
Yes, and now the next one. So its ultrasound can also be detect cracks in blocks of concrete on the grade below. Show the display that would be seen on screen if such a crack were detected.
Okay. Oh, if a crack was detected, there would be a small amount of space there, so it would peak again.
Yes, yes, that's correct.
Okay.
Writing,
So can it be?
yes, yes,
Yeah,
yes.
sorry. It
And
can be like anywhere between the two peaks.
yes, so like yes, definitely
Okay.
a peak between in any these two peaks, anywhere, but in between these
Okay.
two peaks. Yes, you're
Yeah.
correct. Okay, see question 2. Write an account of dispersion of white light in glass in your answer. You should state what is dispersion. Okay, one by one. So what is dispersion?
Dispersion is um, when white light passes through a glass prism, triangular glass prism,
Yes.
and the light the and it's split up into 7 colors,
Yes.
into which is the visible range.
Yes, this is basically dispersion. That's very correct. Now the next
Here,
one
let me just.
is okay, you just write it.
Okay, what causes dispersion? All the lights are refracted at slightly different speeds in the perspex block
Yes.
or in the prism, and so when they come out the other end, like they they're like all split.
So basically it happens because of the reflection.
Yeah.
So actually what happens is if you see a prism, I'm just taking the front part of the prism only. So this is prism. So when this white light enters in prism, what happens is because every color has a different wavelength, right? So these are the
Mhm.
7 colors of white light. So every color has a different wavelength, like R has the highest wavelength and V has the lowest wavelength. So when it enters from rarer medium, this is rarer medium and this is denser medium, what happens is it bends towards the normal, right? This happens. So this white light towards the normal, then this towards the normal, towards the normal, towards the normal, towards the normal. Why? Because of their different wavelength, they bend differently. And that's why ultimately they get split into 7 colors. So when they came out like here, it gets changed or split into 7 colors because of change in density or because of refraction. So what is prism? Prism is basically a device which refracts a light, and same things happening here. White light is being refracted and splits into 7 different colors because all have a different wavelength. And why is so? Because we know that c is equals to lambda time frequency. Okay, so when it
Mm-hmm.
enters from one medium to another medium, because of different wavelength, they enters with different speed, and due to change in speed, they bend differently towards the normal. Okay, and that's why they
Uh-huh.
split into 7 constituent color. That's the reason. Clear? So what causes refraction? So basically, it's the prism which causes the refraction, which causes the light to split into 7 different colors. Okay.
Okay.
And label diagram is that I have drawn, or in more specific manner, like it wasn't the correct one. So you tell me, how can you draw the label diagram for this?
Um, okay, so the label diagram, we need a triangle
Yes.
first.
Yeah. So this is prism. So we represent a prism with a triangle. It's front surface that we take, a 2D one.
Okay, so prism, so a triangle, and then we need a white light coming and striking the block, the triangle.
Yes. So it's like this. I'm just again drawing it in a proper way. This is triangle. This is white
Yeah.
light entering. And since it's entering from rarer medium to denser medium, it will bend towards the normal. Right, so all the colors will move like this. It's somehow this and this. It's like this. We have to draw the 7 lines
Mhm.
representing the 7 different colors.
Do we have to like draw all the 7 lines? I think my teacher told me that we could
Yes, you
just like
can.
get away with.
2 or 3, it's better. Like it's not
Okay.
necessary. If you represents 3, it represents that it's a 7-1.
Okay, so then I'll do like the red and the violet.
Yes, you can take 2-1, like at 2 extreme ends, red and violet will be better.
Hmm.
So you show
Okay.
this, and then again light is moving from denser medium to rarer medium, so it will bend away from normal, then it will bend like this.
So wait, it moves from rare to dense. So in the prism, it'll bend away from the normal,
Yes,
but red is refracted the least, so um it'll only bend away from the normal just slightly,
yes,
and violet will is refracted the most, so it'll bend away more.
yes. So this one is red and this one is violet.
Okay. Okay. So how the apparatus is used. Okay. So you set up a ray box.
Yes.
Um, you shine a thin white ray into it, into the prism,
Yes.
and shine a thin white ray. What would happen if you just if you used a ray box with a yellow light?
So because it will not split, it only gets refracted. Okay, but it will not split.
Okay.
So it's we say it's a monochromatic light, right? Which was some single color. So it's get refracted the same like this. Take only this happens. If I remove all these things,
Mhm.
this happens with the yellow color. But yellow remains the yellow. Okay.
Okay.
Now you explain how apparatus is used.
Okay. The apparatus. Okay, so set up a ray box and shine a thin white ray into a triangular glass prism,
Yes.
um, and the colors and the white ray will be split into 7 colors.
Yes. So you can see that spectrum from red to violet. So red at the very first, and it moved towards the violet at the very lowest one.
Okay.
So that's a basic setup. And observation, here on observation you have to basically write that you have seen that there is a spectrum that color split into the 7 different constituent colors from red to violet. That you have to see because this is the observation. Clear?
Okay, so the white light has split into um, it has split into 7 colors
Yes, which is called
um,
spectrum.
of the visible spectrum.
Yes. Okay, now the next one. Explain carefully what is meant by statement that the critical angle for glass is 42 degrees.
Critical angle for the glass. Okay. Um, the critical angle for the glass. Oh, the critical angle is a certain angle where if you shine the light into it, it'll just like keep getting refracted, and it won't like come out of the other end.
Actually, the critical angle is the angle of incidence for which angle of refraction is 90 degrees.
Okay.
That's
The
basically
angle.
critical angle. Let me just
Okay.
tell you. Wait a second. Tell you. So if I talk about, I'm just taking 3 different cases. When a light is entering from denser medium to rarer medium, okay? So this is
Mhm.
denser and this is rarer. Now this, by red, I'm just representing the normal. And now this is light. So when light enters from denser medium to rarer medium, you tell me what happens.
Um, a denser medium to a rarer medium.
Yes.
Uh,
Like what happens whether it bends away from normal or towards normal.
uh, okay, so from denser to rarer, it bends towards the normal.
It's away from the normal. And how can you
Oh.
remember is that from when you move a light, when light's entering from denser to rarer medium, you tell me what happens with the speed of the light.
Um, the speed of light when it enters a denser medium, the speed of light decreases and bends towards the normal.
Denser is a medium. You see, I'm just drawing a box. Denser is a medium. This is one medium and this is second medium. A denser is a medium where there are larger number of molecules. Density is higher, which means on a particular volume, unit volume, the molecules are higher. So which means it's like this. It has, you can understand in this manner that the molecules are larger over this area, over this unit volume. Okay.
Mm-hmm.
Whereas rarer medium is where molecules are like this. Now, if you try to cross the path, you take an example. These are the two places, and here you can see there are only 5 number of people and there are like 50 number of people, and you want to run. Which place is better for you to run at a higher speed?
Um,
Like this is a very crowded area, and this is a less crowded area,
oh,
less or like
right.
there are only few persons. So, and you
It's
want to
um,
run.
it's easier to run in the area with less people.
Yes, same thing happens. Denser medium is where there are large number of molecules, and rare medium is where less number of molecules. Now, light is just like us. You tell me where light will travel faster.
Um, Light will travel faster at uh,
Rare medium
the,
is a less crowded area. Denser medium
oh,
is more
right.
crowded area, and light is like just like us. You tell me where
Mm,
light will travel faster.
okay.
So tell me where light will travel faster.
Travels faster in the rare medium.
Yes, definitely. So it travels faster and here is slower. That means when a light enters from denser medium to rare medium, it speeds up. Okay. And since it speeds up, so rather than moving like here, it has more energy, so it will move like this. Okay. Clear?
Mm-hmm.
You can understand is like that when you are full of energy, you are more vibrant. You move like this. Whereas if you're less energetic, you're just like this, like that, right? Kind of for analogy. So that means if a light is moving with a faster rate, then it will shoot up like this, and that's why it bend away from the normal, right?
Mm-hmm.
Now the next is if I increase, so this represents the angle of incidence and this represents angle of refraction. Okay, this is I and this is R. Now take another example. If I increase this angle of incidence, say I have increased this. Clearly you can see I have increased angle of incidence. Okay, you can see that I have,
Um,
okay,
yeah.
here. You can see this is angle of incidence. Wait a second. Okay, so I'm saying that here if I increase angle of incidence, you can see that it goes away from normal. Angle of refraction is also increasing, and at one time if I increase angle of incidence way more, this keeps on moving in this direction. You can see that, and ultimately it goes like this. Okay, and now your
Mm-hmm.
angle of refraction is 90 degrees, and this
Okay.
angle of incidence is known as your critical angle. Clear?
Yeah.
So you can see that if you have to describe angle of incidence, critical angle. So you can say the angle of incidence for which angle of refraction is 90 degrees as your critical angle. And why am I explaining you all these things? Because it's very much necessary for you to solve these questions, right? Whenever you solve
Mm-hmm.
these questions, you can clearly see they need you to be some analytically strong, and that's why I'm explaining you the whole thing. Okay.
Mm-hmm.
So actually now you can easily explain critical angle is the angle of incidence for which refraction angle is 90 degrees is the critical angle. And for glass, this angle of incidence is 42 degrees, and that's why this is critical angle. So we'll continue this paper in next lecture. Till then, what you have to do, because we have completed this refraction reflection whole wave, you go through that, revise all that, and we'll continue with this paper. Okay?
Okay.
Okay then. Thank you.
Bye.